Hey there, deep divers. Ready to have your minds blown? Today we're diving into the Banach-Tarski paradox.
Oh yeah, this one's a doozy.
I'm already feeling a little dizzy just thinking about it.
It is a bit of a head scratcher.
So the idea is that you can take a solid object,
Right.
cut it up,
Uh-huh.
and reassemble the pieces into two identical copies
You got
of
it.
the original.
Yep.
Sounds like magic.
It does kind of feel like that, doesn't it?
It's like,
Where'd all the extra stuff come from?
right, where did all that extra stuff come from? I've got a stack of sources here.
Yeah.
Vsauce, academic papers,
Hmm.
even some philosophy folks chiming in,
Oh,
trying to
okay.
wrap their heads around this.
Yeah.
But before we even think about doubling spheres,
Right.
we need to talk about infinity,
Absolutely.
because that's where this whole paradox starts to get really wild.
Most of us think of infinity as just,
Yeah.
well, an infinitely big number,
Uh-huh.
but it's actually more like a concept.
Okay.
The idea of something that never ends.
All right.
And here's where things get crazy.
All right.
There isn't just one infinity.
What?
There are actually different sizes of infinity.
Okay, wait a minute.
Yeah.
Different sizes.
Different sizes.
How can that be?
I know it's a lot.
It's already infinite.
Think of it this way.
Okay.
Imagine you're listing out all the whole numbers.
All right. 1, 2, 3,
1, 2, 3.
4, 5, 6.
Yep. And so on forever.
Okay.
That's what we call countable infinity.
Countable infinity.
You could, in theory, keep counting those numbers one by one,
Yeah.
even though it would take,
Forever.
well, forever.
Yeah.
But then we have all the numbers between 0 and 1,
Okay.
which includes not just whole numbers,
Uh-huh.
but all those decimals, fractions, irrational numbers, like pi.
Oh, man, so many decimals.
Right.
It's like trying to list every grain of sand on a beach.
Exactly.
Okay.
And that's where uncountable infinity comes in.
Uncountable infinity?
It turns out there's so many decimals between 0 and 1 that it's a bigger kind of infinity than all the whole numbers combined.
Seriously?
Seriously.
That's wild.
That's kind of like comparing a thimble full of water
Okay.
to the entire ocean.
All right.
They're both wet,
Uh-huh.
but one is just vastly bigger than the other.
Whoa.
Oh,
Okay, this is already making my brain hurt.
I know. It's a lot to take in.
So how does this idea of different sizes of infinity
Yeah.
lead to something like the Banach-Tarski paradox?
Well, this distinction is crucial
Okay.
because it lets us do things with infinite sets that seem impossible in the finite world.
Okay.
It's like we're playing with a different set of rules.
Oh, right.
And that's the key to the Banach-Tarski paradox.
Gotcha.
It exploits the strange behavior of uncountable infinity to make what seems impossible possible.
All right, so we've got these different infinities.
Yeah.
But Vsauce also talked about a chocolate bar illusion,
Oh, yeah.
where they trick you into thinking you get more chocolate
Right.
just by rearranging the pieces. Is that what's happening with the Banach-Tarski paradox?
Not quite.
Okay.
The chocolate illusion plays on our perception
Uh-huh.
and subtle changes in the size of the pieces.
Right.
But the Banach-Tarski paradox isn't about stretching or resizing anything.
Okay.
It's purely about rearranging pieces based on this idea of uncountable infinity.
Okay, so no sneaky chocolate bar tricks.
No sneaky tricks.
But this still feels like we're breaking some fundamental laws of reality.
It does seem that way.
Like, stuff can't just appear out of thin air, right?
It does, it does.
But-
But to truly grasp how this works,
Yeah.
we need to embrace the fact that infinity can lead to some seriously counterintuitive results.
Okay.
Take Hilbert's Hotel, for instance.
Hilbert's Hotel.
Yeah.
Is this a real place?
Yeah.
Because I'm ready to check in.
It's a thought experiment.
Okay.
A hotel with an infinite number of rooms.
All right.
Every single room is full.
Okay.
But then a new guest arrives.
Oh.
In a normal hotel, they'd be out of luck.
Yeah.
But in Hilbert's Hotel,
Okay.
they can simply move the guest in room 1 to room 2,
Okay.
the guest in room 2 to room 3,
All right.
and so on infinitely.
Wait, so you're telling me that
Yeah.
even though every room is already occupied,
Huh.
you can still fit in more guests
You got it.
just by shuffling them around?
That's right.
How does that even work?
It works because with infinity, you never run out of room.
Mind blown.
It's like adding one more grain of sand to an already infinite beach.
Okay.
You're technically adding something,
Yeah.
but it doesn't change the overall fullness of the beach.
Okay.
And this principle applies to more than just hotel rooms.
Okay, now I'm really confused.
I can understand that.
So infinity means we can always squeeze in more stuff.
In a way, yes.
Even when things seem full.
That's the thing about infinity.
It's like the rules of logic just fly out the window.
It's definitely a shift in thinking,
Yeah.
But these seemingly impossible ideas
Okay.
are crucial to understanding the Banach-Tarski paradox. It challenges our everyday intuitions about how the world works
Right.
and forces us to confront the strange and wonderful possibilities that emerge when we start dealing with infinity.
All right, so I've got different sizes of infinity,
Yeah.
hotels with endless rooms, and this is just the beginning.
Well, we're just getting started.
Why I have a feeling we're about to dive even deeper into this mathematical rabbit hole.
You're absolutely right.
Oh, boy.
Next, we'll explore a fascinating analogy,
Okay.
a dictionary that contains every possible word
Whoa.
to see how parts can be manipulated to represent the whole,
Okay.
just like what happens with the sphere in the Banach-Tarski paradox.
A dictionary with every single word.
Every single one.
Now that sounds infinitely interesting. I can't wait to hear more.
Let's do it.
Let's dive in.
All right?
Okay. My brain is still buzzing from that whole infinite hotel thing.
Yeah, infinity does that to you.
But you mentioned a dictionary with every single word.
Right.
That sounds just as mind-boggling.
It is. It is.
So what is this dictionary?
It's called the Hyperwebster,
Hyperwebster.
and it's a thought experiment
Okay.
by mathematician Ian Stewart.
Gotcha.
Imagine a dictionary containing literally every possible combination of letters you could create,
Okay.
from A to Zizava and everything in between.
Wow. So every word ever.
Every word imaginable, yep.
And how big would this dictionary be?
Oh, it'd be massive.
Huge.
Unimaginably large.
And what are we doing with this dictionary?
Okay, so let's focus on just the A volume of this massive dictionary.
Okay, the A volume.
Yep.
So like all the words that start with A.
Exactly. But here's the kicker.
Okay.
If you were to remove the first A from every word in that volume, you'd be left with every other possible word.
Hold on. So you're saying
Yeah.
that by removing the A from the beginning of each word in the A volume,
Yep.
we'd end up with the entire dictionary again.
That's exactly what I'm saying.
How is that even possible?
Because every word,
Yeah.
whether it starts with A or not,
Okay.
exists within that A volume.
Right.
Once you take away that initial A, it's a bit like a hidden code within the dictionary itself.
Wow. That's incredible.
Yeah, it's pretty neat.
So how does this dictionary idea relate to the Banach-Tarski paradox?
Okay,
So doubling a sphere.
it illustrates a crucial concept,
Okay.
how parts can represent the whole,
Right.
even in seemingly impossible ways.
Okay.
Just like removing the A from the A volume gives you the entire dictionary.
Uh-huh.
Certain manipulations of the sphere's parts can result in a representation of the whole sphere.
All right. I think I'm starting to see the connection here.
Good,
But how do we apply this dictionary trick to a 3D sphere?
well, we're not removing letters,
Right.
but we are going to name and categorize every single point on the sphere's surface.
Every single point.
Every single one.
But there are infinitely many points on a sphere.
That's right, which is why we'll use an infinite process.
Okay, so how do we do that?
Imagine we pick a starting point on the sphere. Then we define other points based on how we rotate from that starting point.
Rotate.
We'll use 4 basic rotations,
Uh-huh.
up, down, left, and right,
Okay.
each along a fixed axis.
So if I rotate up, right, down,
Uh-huh.
that sequence of rotations would define a unique point on the sphere.
Exactly. And a different sequence like left, left, up
Okay.
would define another unique point.
So we can create unique names for points
You got it.
based on these rotation sequences.
That's the idea.
But are there any rules to this?
There are a few.
Okay.
We can't backtrack like doing left then right,
Okay.
because that would just bring us back to where we started.
Right, right.
And we need to consider every possible combination of these rotations.
So it sounds incredibly complex.
It is, but stick with me.
Okay.
So essentially, we're creating an infinite list of names
Yeah.
for all the points on the sphere
Yep.
based on these rotation sequences.
Gotcha.
But to further categorize these points,
Okay.
we're going to add color coding to the mix.
Color.
Yeah, for example,
Okay.
all points reached by a sequence ending in left might be colored purple.
Purple.
All
Okay.
those ending in up might be orange, and so on.
So each point gets a unique name
Right.
based on its rotation sequence.
Yep.
And a color based on the last rotation in that sequence.
Exactly.
Gotcha.
But there's one more thing.
Okay.
What about the poles of the sphere?
The poles. Oh, yeah.
They create a bit of a problem.
Why is that?
Well, the poles are special because you can reach them with different rotation sequences.
Okay.
If you're spinning around the North Pole, left, up,
Yeah?
might end up at the same point as up, left, which could mess up our naming system.
Right, because we want each point to have a unique name.
Exactly.
So how do we deal with the poles?
We treat them as a separate category.
Okay.
Instead of using rotation sequences, we'll give them their own unique color.
Right.
Say yellow.
Yellow poles. Got it.
Yeah.
So we've got our yellow poles and then all these other points on the sphere, meticulously named and color-coded.
There's that.
Based on their rotation sequences.
Yep.
It sounds like a very elaborate paint-by-numbers project.
It does a little, doesn't it?
But what's next?
So here's where the dissection comes in.
Okay.
It's not a physical cutting.
Right.
It's a conceptual division based on the names and colors we've assigned.
So we're not actually cutting up the sphere.
No, not physically.
Gotcha.
Think of it like sorting a giant bag of Skittles based on color.
Okay.
But instead of Skittles,
Yeah.
we're sorting points on a sphere based on their rotation names and colors.
So we haven't actually changed the sphere physically.
No.
We've just organized the points in our minds based on this elaborate system.
That's right.
But it's still one whole sphere, right?
Absolutely. It's all one sphere.
Okay, good.
But now we've got it categorized into these specific abstract pieces
Yeah.
based on their rotations and colors.
All right.
And this is where the real magic of the Banach-Tarski paradox begins.
Oh, boy. Here we go.
We're going to focus on one of these pieces.
Okay.
Say the one containing all the left points.
Purple points.
Our purple points, yeah.
Okay.
And see what happens when we rotate it.
We're rotating just the purple piece.
Yep.
So what happens to all those points?
When we rotate the entire purple piece to the right,
Okay.
we're essentially adding an R to the end of every single point's name
Uh-huh.
within that piece.
Okay.
But remember,
Yeah.
left and then right cancel each other out.
Right.
So when we simplify those names,
Okay.
the left piece, after being rotated, suddenly includes points that were originally up, down,
What?
and even some of those starting points.
Wait a minute.
Yeah.
So by rotating just one piece, we've somehow expanded it to include points that were originally in other pieces.
You got it.
It's like multiplying our purple Skittles just by moving them around.
That's a great way to think about it.
So this is like a volume of the Hyperwebster all over again.
Exactly.
By manipulating a part.
Yeah.
We're somehow accessing a much larger portion of the whole.
That's right.
Okay, I'm starting to see how this could lead to doubling a sphere.
You're on the right track.
But we've only rotated one piece.
Well, we can repeat this process with other pieces as well.
Oh.
For example, if we take the up piece and rotate it down.
We'd end up with a piece that includes all the up, right, and left points.
That's right.
Plus some of those special starting points.
You're getting it.
It's like we're rearranging the recipe of the sphere
I like that.
to bake two spheres instead of one.
That's a perfect analogy.
So by strategically rotating and rearranging these pieces, we can, in a mathematical sense, create two sets of points that each correspond to a complete sphere.
Exactly.
This is blowing my mind.
It is mind-blowing.
It sounds like we're not creating matter out of nothing,
Right.
but rather we're rearranging existing points
That's it.
in this incredibly clever way
Yeah.
that takes advantage of the peculiarities of infinity.
Precisely.
The Banach-Tarski paradox highlights that our everyday understanding of volume and solid objects breaks down
Right.
when we venture into the realm of infinite sets and perfect mathematical precision.
You got it.
Okay, so we've dissected our sphere,
Yes.
rearranged the pieces using rotations, and somehow ended up with two sets of points
Right.
that each represent a whole sphere.
That's the Banach-Tarski paradox in a nutshell.
But this is all just mathematical theory, right?
Whoa.
Can we actually double a real physical object using this method?
That's the million-dollar question.
Like, can I take a gold coin,
Yeah.
cut it up according to these rules,
Right.
and end up with two gold coins?
It would be amazing, wouldn't it?
Because that would be pretty amazing.
That's the question we'll tackle when we return.
Okay, so back to that million-dollar question.
The gold coin question?
Yeah, can I double my gold?
Well, I can understand why you'd want to double your gold.
Who wouldn't?
But like most things that seem too good to be true, there are some catches when it comes to applying the Banach-Tarski paradox in the real world.
Okay, so why can't I become a gold duplicating magician?
Well, the first issue is precision.
Okay.
The Banach-Tarski paradox relies on infinite precision.
Right.
Remember how we named every single point on the sphere
Yeah.
based on those infinite rotation sequences?
Yeah, it was like a giant jigsaw puzzle, but with infinitely many pieces.
And how those pieces fit together perfectly without any gaps or overlaps.
Right, exactly.
In the real world, we can't achieve that level of precision.
Huh.
Our tools, Our measurements, even the atoms that make up matter, have limits.
So it's like trying to draw a perfectly straight line.
Exactly.
You can get close, but you're always limited by, like, the sharpness of your pencil.
Yeah, or the resolution of your eye.
Exactly.
You can only get so close.
So even with the most advanced 3D printer or laser cutter, we couldn't create those infinitely intricate pieces required for the paradox to work. Our real-world tools are just too clumsy for this kind of mathematical magic.
It's true. We're limited by the physical world.
Yeah.
And there's another crucial point.
Okay.
The paradox deals with purely mathematical objects.
Okay.
Not physical ones.
Right.
In mathematics, a sphere is a collection of points. But in the real world, a sphere is made of atoms.
Ah, right. Atoms.
Yeah.
I forgot about those little guys.
Tiny, but important.
They have their own rules about how they behave.
Exactly, governed by physics.
Right.
It's not just a collection of abstract points.
So even if we could somehow overcome the precision issue, the paradox might still not apply to real objects.
Right.
Because they behave according to the laws of physics, not just the rules of abstract math.
That's a key insight.
Okay.
However, there's one area where the paradox gets really intriguing.
Oh. Tell me more.
Some physicists have suggested it might have connections to the bizarre world of subatomic particles.
Subatomic particles?
Yeah.
The stuff that makes up atoms.
The very same.
What do they have to do with the Banach-Tarski paradox?
Well, at extremely high energies, like those found in particle accelerators, particles can collide and create more particles than we started with.
So like matter from energy?
Kinda. It's like a subatomic version of the paradox.
Okay.
Where rearranging and transforming particles can lead to an increase in the overall number of particles.
So you're saying there might be a deeper connection.
It's possible.
Between this seemingly abstract mathematical idea and the fundamental nature of reality at the subatomic level.
It's a fascinating possibility.
Wow.
It suggests that maybe our understanding of stuff and how it behaves is still incomplete.
So we still have a lot to learn. Perhaps the universe is far stranger.
Absolutely.
And more counterintuitive.
Definitely.
And then our everyday experiences lead us to believe.
That's one of the things I love about physics.
Well, this whole deep dive has been a wild ride.
It has been fun.
We started with a simple question about doubling a sphere.
And look where we ended up.
And ended up exploring the depths of infinity. The quirks of set theory. And even the mysteries of subatomic particles.
It all connects somehow.
So while we might not be able to double our gold coins,
sadly,
using the Banach-Tarski paradox,
not yet anyway,
we've certainly gained a whole new perspective.
That's what we hope for.
On the nature of infinity, mathematics, and perhaps even reality itself.
Absolutely.
Thanks for joining us on this deep dive into the Banach-Tarski paradox.
It's been a pleasure.
It's been a truly mind-expanding journey.
Always happy to chat about infinity.
And for all you deep divers out there,
keep on diving.
We've included some links in the show notes.
To learn even more.
To articles and videos that explore these concepts further.
Definitely check them out.
Keep questioning, keep exploring, and keep your minds open.
To the wonders of the universe.
To the infinite possibilities of the universe.
The terrestrial